Hello ECE 205. Last time we left on a cliffhanger, so let's get into it. So for this lecture we have two goals. The first goal is to continue our discussion for second order linear homogeneous differential equations with constant coefficients and to analyze those three different cases depending on the value of the stuff under the square root. And then after that we are going to examine differential equations of this form where f of x is now non-zero. So explicitly, linear second order non-homogeneous differential equations. Okay, so let's go to work. Okay, so the first thing that we're going to do here is continue from our previous discussion. So recall from last lecture that if we restrict our attention to differential equations of this form, where a, b, and c are all constants, and in particular, a can't be zero, otherwise we only have a first order equation, and we already know how to solve that, then we can readily find two solutions that may not be linearly independent or may not even be different from each other, as we'll see. Explicitly, these two solutions we found were this y1 and this y2 that are of the form e of the lambda plus or minus times x, where lambda plus or minus satisfies this characteristic equation here, where this polynomial p of lambda is simply found by taking this thing here and replacing the various derivatives with various powers of lambda. Again, remember, basically the way that we found this polynomial was plugging in this ansatz into the differential equation and then noting that the exponential term cannot be zero, therefore the polynomial term must be. Okay, so from here we're going to do three cases based off the sign of this term that's under the square root. Okay, so let's jump in. So for the first case, we're going to assume that this thing is greater than zero. Now, if this is greater than zero, what do we know about the roots of this polynomial? Well, from the quadratic equation, we have negative b plus or minus the square root of this thing all over 2a. So if this thing's greater than zero, that square root is going to be greater than zero when I evaluate it out. So I'm going to have two real roots, lambda plus and lambda minus. Okay, so from here, I could simply compute y1 and y2 by computing these lambda plus and lambda minuses and put them into that functional form that we found earlier. Now, in this case, because I have two different roots, y1 and y2 are actually two different solutions. Okay, that's kind of nice. Our kind of overarching goal was to find the general solution, and we know from some of the theorems we showed in the last lecture that to find the general solution, all we need is to have two distinct solutions that are linearly independent from each other. Okay, so let's use one of those theorems to try to show that these are linearly independent, or show that they're not. Well, note that the assumptions that we have on this differential equation are the same assumptions that we need in theorem 5.1.6. So those assumptions hold, and thus that theorem is valid. So now what we can do is we can simply compute y1 divided by y2. Notice that that would be explicitly this term over this term, where lambda 1 and lambda 2 are different from each other, and a direct computation gives us that this will simply be single exponential of this term, where this thing is not equal to zero. That means this thing is not constant, as in it varies with respect to x. Okay, so from here we can finally conclude that this thing from theorem 5.1.6 must now be linearly independent. Or that doesn't come from theorem 5.1.6, that comes from the fact that they're non-constant. And therefore, from theorem 5.1.6, we can conclude that this is a fundamental set for the differential equation that we started solving. So here, 5 is referring to the original equation from the last lecture. I will change it to 1 to fix that. Okay, so from here, the general solution would just be an arbitrary linear combination of these two linearly independent functions. Okay, so that case is done. Let's go to case 2. So case 2, I'm going to start with the case where this thing is negative, and then I'm going to work with the case where it's 0. It's slightly different order than in the text, but I think this is kind of a little bit of an easier case than case 3. Okay, so if this thing is strictly less than 0, then from the quadratic equation, I know that I have two complex conjugate roots, and these roots explicitly, lambda plus or minus, will be in this form here, where we can assume, without loss of generality, that omega is greater than 0. Okay, so if omega is less than 0, I just get lambda minus plus. It doesn't change anything. Okay, so from here, since these are two distinct roots, this function here and this function here, where I plug in those complex numbers, well, yeah, that might not be real valued, but we know these are going to be distinct solutions, if in fact they are solutions, despite the fact that they're not real valued. Okay, so let's examine these in a little bit more detail by using the fact that we know the functional form for lambda. Okay, so but notice that e to the alpha plus omega I, and immediately just using properties of exponential rules, we simply get that this will simply be the product e to the alpha times e to the omega I. Okay, so now we've actually seen this before in, say, Math 115. E to the omega I, we can use Euler's formula to rewrite this thing out as this cosine of omega x plus I sine of omega x, where here this is a alpha instead of an a. Okay, so in fact, looking at this, we know for certain that this function here is not going to be real. So this is totally unreal. Okay, but what we can do is we can examine these functions, namely this term here and this bit times this bit here, where we ignore the I, and we can see what happens. Okay, so if we examine these particular functions here, it might be the case that this potentially solves the differential equation, right? We know that if I have two solutions to a homogeneous differential equation, then the sum solves the equation itself. So here, this, at least mechanically, would solve the equation. So let's see if I replace this I with 1. Let's see if that works. Okay, so a pretty direct computation, basically plugging these in the differential equation, shows that these are actually solutions to the differential equation. Okay, I'm not going to do this computation because it's just computing two derivatives, plugging it in, but do it to verify that it works. Okay, and furthermore, if I take the ratio of these two functions, y2 divided by y1, that just simplifies to sine of omega x over cosine of omega x, right? The exponentials cancel. Okay, and then from here, that is tangent of omega x, which clearly is not a constant. Okay, that means that these two functions solve the differential equation from our exercise and are linearly independent. Therefore, by that theorem 5.1.6, we can say that these things are linearly independent and therefore a fundamental set. So in this case, the general solutions are written as an arbitrary linear combination of these functions here, where I will fix the a and replace it with alpha now. Okay, so this is kind of an interesting problem if you actually think about it. We started with something completely real valued, a real valued ordinary differential equation where everything was real. We went to try to find a solution. We end up going to the complex number system to find something that kind of works, but it's complex. But then we can use this solution within the complex number system to find a real valued solution. So it's kind of one of the classical applications of complex numbers to the real world problems. We can often use them as an intermediary step in order to find a solution that we wouldn't have been able to find otherwise if we didn't know complex numbers. Okay, so we have one more case to go. What about the case where that is exactly equal to 0? Well, in this case, we only have one root. Namely, we have a root that is repeated twice, and that will simply be lambda 1 is negative b over 2a. Okay, this is kind of problematic since we now only have one solution. This term here, y2, is the same thing as y1. Therefore, if I take the ratio of the functions, it's going to be 1. 1's clearly a constant, so I don't have enough solutions to find my linearly independent set of two solutions. Okay, that's kind of awful, but is there a way that I can find another solution given this first solution here? Well, yeah, we have that one theorem on lecture 14 from the last lecture, and why don't we use that to try to look for a solution of this form, where here this is the functional form of the second solution that I found that was guaranteed to always find, given that this thing here is properly integrable. So I can use this to try to find a solution. Okay, so let's just do some straightforward calculations. Okay, here, if I want to plug everything in, my p of x, well, my polynomial, what did that thing look like? Well, if I just go back a few slides, this is what my polynomial looks like. Well, lecture slide 14, that didn't actually apply for differential equations of this form. It only applied for differential equations of the form y double prime plus some p of x, y prime, plus some q of x, y is equal to 0. So I can't use this theorem directly to this function, or this differential equation. I have to divide it by a. So dividing by a gives me that b divided by a is simply going to be this p of x function, okay? So there I replace the p of x with this thing here, and I just want any antiderivative here. I ignore the constant, just to talk about an arbitrary antiderivative. And then I want to divide this whole thing by y1 squared. Well, y1 would simply be e to this power, so that's my y1, and that's squaring it. Okay, so here, if I integrate this thing, that just gives me b divided by a times x, so I get my exponent here, and here, when I square this, I simply get this, okay? So from here, these are the same functions, it's the same values, therefore I know that u has to be equal to 1, or sorry, u prime has to be equal to 1, and integrating gives me u is equal to x. And again here, I don't include that arbitrary constant, because I don't really need to include the arbitrary constant here. I just want to find a single solution, y2, and then I'm going to scale it by an arbitrary constant at the end. Okay, so now that I know what u is, I can just plug back into this functional form here for y2, and I can say y2 is clearly going to be equal to x e to the lambda 1x, where we could do the substitution here if we wanted. Okay, so we have that this thing is going to be a solution to the differential equation 1. Good exercise would be to check that this is in fact the case. It is, but it would be good to verify, good practice there. So now what have I done? I have a new solution y2, and I have this other solution y1. The natural question is, do I now have a linear independent set of two solutions, or are these two things linearly dependent? Well, to check for linearly independence, we take y1 divided by y2, we notice just this quantity here, and these are the exact same term, so I just get x. X depends on x. This is not constant. That tells us that this thing will be a linearly independent set, and therefore a fundamental set of solutions. Okay, so now we have gone through all of the possible cases that we could get here. It turns out that this particular case is a good class of solutions just to memorize what the solutions are, because you're going to be using these a lot, and it's a really classical solution. So in worst case scenario on a test or something like that, it would be a good idea to know how to analyze these cases and how I found the solutions to be of this form, that whole eigenvalue stuff that I did. But at the end of the day, we can put this in a theorem, and you can cite that theorem to find these solutions. So let's give you a theorem from the lectures. Okay, I'm just going to put it all up at once and just kind of skim over it. Okay, so if we have a differential equation of this form, we're going to simply let p of r be of this form, be the characteristic polynomial for that differential equation. And then we're going to find the roots. So depending on what type of roots we found, we're going to have general solutions of different forms. So if we have two distinct roots, then all we have to do is plug it into this functional form here, and there we go. If we have a repeated root, then we're going to find a general solution in this form here. So note here I just factored out this e to the r1x. This is kind of the classic way of writing this functional form, and as you'll see, not in this lecture, but in the next lecture, functional forms of this form here do actually tend to pop out a lot. And then finally, if we have complex conjugate roots of this form, then the general solution will be given by of this form here. Okay, so just one comment on the complex conjugate case. Notice that what we're really doing here in the previous work and here is we're just saying that the real part of what we found for one of these y1 functions is one of the functions that goes into my fundamental set, and then the imaginary part is the other one. So generally speaking, one way that you might see this written in, say, literature is to actually use the complex exponential and talk about the real part and the imaginary part. Okay, so just to spill that out analytically, you could write this, like so. And in other cases, like higher order differential equations, you end up with the same type of phenomena happening whenever you have these complex conjugate pairs. And generally speaking, thinking of it like this can be useful, but for this class, I do want you to just use this functional form here. Okay, so that's not bad at all. I'm going to skip over examples of actually applying this theorem. They're pretty straightforward. You just find the roots and do the stuff. There are examples in the text, and if you do want to see examples of working this out, then check those out. But generally speaking, you just say, this is what my characteristic polynomial are, these are what my roots are, therefore the solution is, put whichever one of these it is. Okay, that is that case completed. So now we're going to turn our attention to extending those theorems that we had in lecture 5 that were only valid for differential equations of this form, to the broader class of forced differential equations of this form. So again here, this is a forcing term. It's non-homogeneous first order linear differential equation with non-constant coefficients. Okay, so the first kind of low-hanging fruit, we started lecture 5 by talking about that theorem 5.1.1 for the existence of a solution to the initial value problem. So we have an analog theorem here. So existence and uniqueness can be extended. Explicitly, if P, Q, and F are now continuous on this open interval here, and x naught is any point in this open interval, and I pick these two arbitrary real numbers k0 and k1, then this initial value problem has a unique solution on AB. So the only difference between this theorem and theorem 5.1.1 is that we're now extending the possible values that the f of x function can take on from 0, like it was in 5.1.1, to now any arbitrary continuous function on this open interval. Okay, so just some notes here. This theorem is actually proved with the help of theorem 5.1.1. That's why this thing was introduced first, but like with 5.1.1, we're not going to prove this because it is a bit beyond the scope of the class. But instead, we're still going to note that the comments that I made for 5.1.1 are still valid here. That is to say, when you actually go to prove this theorem, you can't actually find the solution or a functional form for the solution. You simply show that it exists, and thus you don't actually have a clean way that you can always construct solutions to these type of functions. Okay, so alas, you're still stuck with kind of dealing with differential equations on a case-by-case basis, and there's no general jack-of-all-trades method that will solve all of these. There are some that solve very large classes of them, but there's none that works for everything. Okay, so you've seen how this theorem works in a previous example, so I'm not going to do an example of this theorem here, but it's basically analogous to what we did before, other than you need to find an interval of which P, Q, and F are all continuous to find these unique solutions. Okay, so previously, when I try to solve equations of this form, the non-homogeneous equations, we first found solutions to the homogeneous equation, and then we used those to assist trying to find the particular solution over here. Namely, we did the variation of parameters when solving linear first-order differential equations that were non-homogeneous. So it turns out that for second order, we use a similar type property here. Okay, so let's introduce a theorem for the existence of a general solution here. So suppose P, F, and Q are all continuous on an open interval AB, and suppose that I can find a particular solution of this differential equation on AB. Okay, here I might not actually be able to find this particular solution. It does exist, but I might not be able to find it in practice. But yeah, so this thing exists. And if we let this y1, y2 be a fundamental set of solutions to the complementary equation, this thing here. So recall we actually talked about complementary equations when we did first order differential equations. So the same idea here works. If I have a non-homogeneous differential equation, the homogeneous version of that differential equation is the complementary equation. So anyways, if I have this fundamental set of solutions here, then y is a solution of 3 on this open interval AB, if and only if y can be written in this form here. Okay, so here I'm taking the particular solution that I found up here, and to that I'm adding this general solution to the homogeneous version of the equation. Why do I need to do this? Well, in general, this particular solution that you find up here, it's going to turn out that that solution usually doesn't have free parameters. Usually, as in it never has free parameters, assuming you picked the kind of cleanest, nicest, most refined particular solution that you could find. Thus, if I ultimately want to solve an initial value problem, I need to have free parameters, in particular 2 of them, because I have a second order differential equation, to be able to satisfy the initial conditions. Okay, so this solution here actually has a name. We call solution y with these properties the general solution of 3 on this interval. Note this nomenclature is different than the general solution we talked about for linear first order differential equations. So in the case of linear first order differential equations, we know that there's going to be a solution defined everywhere, given that the differential equation can be written in, ignore these terms here, this form here where q is continuous. So the general solutions there, we want to work for absolutely all initial value problems for all values of x. But here, this can be a general solution on some interval AB, where we're forced to restrict this interval because we may not have a solution on a bigger interval than this. Okay, so TLDR, we have general solution of a differential equation, which is going to be a solution that would solve all initial value problems for that differential equation that you could possibly do. And we have the general solution of a differential equation defined on an interval, AB, or open interval. And this is going to be kind of a simplified version of a general solution, restricted to an interval smaller than all real numbers. Okay, now that we've given us a new theorem, the natural question is, how do you go about proving this theorem? So here, I'm not going to go through all the details. They're not particularly bad, but there's a lot of little algebra to go through. So instead, what I'll do is I'll go through the proof in trench, and I will point out the key ideas that require a little bit of thought, and then just say, yeah, here we just do some direct computations, where we just do direct computations. Okay, so in general, if I want to show that this thing is a solution to 3 on AB, I need to show that if I take this function and plug it into here, it satisfies the equation. So if I'm doing that for the backwards direction, all I have to do is take the first and second derivatives, plug them into here, and see that everything simplifies. So that's exactly what is done here. Okay, so here if I take the first derivative and the second derivative, and let me switch this up. Okay, so side by side just to make it a little bit cleaner. So here I take the first and second derivatives, and then all I do is I take this differential equation, I plug these into the differential equation, and I simplify it out. So the key ideas here is that since these are a fundamental set of solutions to this complementary equation, I can isolate for bits where I have something that looks like this equation here, or this left-hand side of this equation here with y1 replacing y and y2 replacing y respectively. And then when I get those terms, I just get 0 and it all cancels out. So that's where I get this thing here where I get these zeros wiping out. So pretty straightforward, just do the algebra type proof. Now, the other direction is where you have to be a little bit more clever. Okay, so there I'm saying if y is a solution to 3 on AB, then y has to be able to be written in this form here, where this y sub p is just some particular solution here. Okay, so we don't have a super nice way to identify these y sub p's, right? In general, there is none. So we're kind of stuck with working with an arbitrary function y that solves this. So how do we go from that arbitrary function to it has to look like this? Well, what we can do is this nice little trick here. We say, hey, suppose y is a solution to the original differential equation, okay? If y is a solution to this equation up here, then if I subtract yp from it, if I can end up with something that is of the form c1y1 plus c2y2, then I could simply solve this for yp and show that y has that functional form. Okay, so I'll make the text bigger here so we have a better picture, and we'll go from here. Okay, so if y minus yp is a solution to the homogeneous equation, then since by our statement over here, we know that this y1, y2 is a fundamental set of solutions for the complementary equation, then we know that since this is a solution to that complementary equation, then it has to be able to be written as a linear combination of y1 and y2. Okay, so if this is a solution of the homogeneous equation, then I have that it's written of this form, and I'm done. Okay, so now all I'm going to do is I'm going to take this y minus yp and then plug it into this differential equation here. Okay, so that's where I get this term here. That is just taking this and plugging it into the left-hand side. And then note, I'm not saying this is equal to 0 at this point. I do some computations and show that it has to be 0. So computations are pretty straightforward. Just distribute the derivatives at this point, and then after you distribute the derivatives, collect the terms in terms of y and p as such. And then from here, we know that y is a solution to the non-homogeneous problem. So from here, we know this thing has to be equal to f of x, and we also know that this y of p is a solution to the homogeneous problem as well. Could be the same thing as y, could be different. It's just some arbitrary solution. Therefore, this thing, when I plug it into the differential equation, this thing here has to simplify to f. Thus, f minus f is 0, and therefore we have that this y minus p is in fact writable as this linear combination. Solve that for y. Okay, that's the basics of what's happening there. I might have went a bit quick on that just because it's a video and you can always rewatch. But if you have questions there, feel free to ask me and we can cover it in office hours for a bit more of that one-on-one interacting with it, because it is kind of a tricky proof at that point. Okay, so from here, we now have this notion of a general solution extended to second order non-homogeneous differential equations. Okay, so we had it for first order equations. We could sometimes get it for nonlinear equations. Usually it would break down for some initial conditions. And then we had it for homogeneous second order, and now we have it for non-homogeneous second order equations. Okay, so generally speaking, what you're going to do with the problem, if you try to solve it, you're going to try to use this theorem to solve first this complementary equation, and then try to find a particular solution. Okay, that's all well and good, but I have not told you any possible ways of solving these type of equations. So let's first start looking at these equations where this f of x term is simply some arbitrary function that we'll pick, and these terms here are going to be constant. Okay, so let's start out with this beautiful problem here. Find the general solution to this, and ultimately use your solution to solve this initial value problem. Okay, so here I'm kind of starting with the simple case where I put 1, just to let us dip our toes in the water, so to speak. But later on at the end of this lecture, we will do an example that's a bit more involved with the more complicated function f. And do recall, in general, if I really plug really bad functions in here, I can give you differential equations that you can't actually find a solution. So ultimately, we're still going to have to be kind of restricted on what we examine. Okay, so let's talk to Mr. Paint and look at this question. Okay, so to solve this question, to find the general solution, so GS for the general solution part, I first need to solve the homogeneous problem, right? If I go back to my previous theorem, to find the general solution, I need to find this bit here, okay? So we could go through and rehash all the arguments for trying to solve this from scratch, but we have that nice theorem, and feel free to use this theorem, but you should know the proof because I might ask you to say, prove one of the cases on the midterm or the final, right? So you should be aware of that proof. That's fair game for tests, assuming they go in person. If it's online, you can just look it up in the notes, so I won't do that, right? Okay, so from here, if I want to solve this thing, I first need to find the zeros of the characteristic polynomial. So what is the characteristic polynomial? Well, it's just going to be r squared coming from this term with the 1 in front of it, plus 1. Okay, so I want to find when this is 0. Well, directly examining this, from here I know r has to be equal to plus or minus I. Okay, so I'm in that kind of third case or second case, depending on if you look at my lecture slides or that one theorem. And here I'm going to have solutions in terms of potential exponential bits and sines and cosines. Okay, so here if I stick with that particular form that we had for the solution there, in that theorem, we would simply get y is equal to e to the 0, y is equal to some constant times e to the 0x, right, because I have no real part. This bit goes away, right? So I'm going to suppress that. And then in terms of the sine and cos, or the trig terms, here I would have a cosine of x, and then plus a c1 sine of x, okay? So there's no exponential, or sorry, c2 here. So there's no exponential bit to this because the real part was equal to 0. Okay, so now that bit's done. Now I somehow need to find a particular solution to this. We haven't shown a technique for finding particular solutions for these, but we can take this whole idea of an ansatz that we've used for other questions to try to find the solutions, and we can use that here. So if you look at this solution, if you just look at it, here I want a function such that if I take its second derivative and then I add it to that function itself, I get 1. Can I think of a function that has that property? Well, if y is equal to 1, then if I plug it in here, I get a 1. And when I take its second derivative, it goes away. So if I let y be 1, that gives me a particular solution. Okay, so from here I can say yp equals 1 by inspection. Now, as a student, this would immediately beg the question, can I do this? No, you can't do that for this course because it's impossible to tell if you could think through your process for why it was true, or if you just typed it on the internet and found the solution. But don't worry, we will give you a method. Well, before this lecture is over, we will give you a method to find particular solutions to things that are kind of this form, where you replace the 1 with a polynomial, and you can just use that method here, okay? So if you wanted to do something by inspection, you would have to write out all of your thought processes for why that solution would work, and it has to be a thought process that you reasonably could come across by looking at it and thinking. So just try to avoid by inspection and try to use the particular methods that we'll give here. Okay, so if we put all these together, I have that the general solution is simply going to be, so general solution is this y, and I'll put a g to make it clear that I want the general solution, the particular solution, plus this thing here, where c1 and c2 are arbitrary constants, and you don't really have to state that they're arbitrary constants here because they're always going to be, so that's something you can take for granted here. Okay, so the next thing I want to do is I want to solve the initial value problem. So how do I go about doing that? So for the second bit, IVP. Okay, so I just want to take these things and apply them here and then find out what happens. So if I do this, what happens? Well, the first case was that y of 0 is equal to 2. So in this case, I simply write 2 is equal to 1. So cosine of 0 is 1, so 1 plus c, 1, plus sine of 0 is 0, so from here. I can simply say, hey, c1 is equal to 1. Okay, so next up, I want y prime of 0, and I want this to be equal to minus 7. Okay, so here I really want you to take the derivative to show me, yeah, that's what we get. So here you would say yg prime is equal to, well, the derivative of cosine is negative sine, so minus c1 sine of x. And if you wanted at this point, you could use this fact here. You don't need it, so I'm just not doing that here. Plus c2 cosine of x. Okay, so from here, I would thus have negative 7, if I evaluate this point, is equal to minus c1. Oops, sorry, I flipped it up, c2. And I flipped it up here. That's should be a plus 7. Okay, so from here, and that's a plus, there we go. So from here, I get c2 is equal to 7. So my oopsies with the negative signs was because I was looking at the solution on the other side to make sure I didn't screw anything up, and made an error with the negative 7. So yeah, so here's the proper way to do it all the way through. Okay, so from here, if I take these and plug them in, the solution that I wanted is now y is equal to 1 plus cosine of x plus 7 sine of x. So there is my solution. Okay, so cleaning it up and then putting it into the lecture slides. So from there, that's our solution. If you want to see it worked out in a slightly different way, you can see that exercise in the text. Okay, so now before I go through and talk about a general method of trying to solve these type of particular differential equations where I change the one to be, say, a polynomial, let's give a theorem that will help us dramatically when trying to solve these types of equations. Okay, so another useful theorem. So suppose P1 is a particular solution to this differential equation on AB, and that y of P2 is a particular solution to this on y of AB. So the difference is I have these different forcing terms here. Okay, well, if this is the case, then if I add those two particular solutions together, that will give me a particular solution to this differential equation on AB. Okay, this is pretty trivial to do. All you do is you assume this premise up here and write y of p of this form. Then you take this y of p, plug it into this thing here, and then simplify out to get basically this thing in terms of y of p1, which you replace with f1, and this thing in terms of y of p2, which you replace with f2. That's the basic idea, but for the details there, see trench. I'm not going to go through it. It's very short. Okay, how does this help us? Well, if I were to give you something that's like find a potential or a particular solution to something of this form, you can now make your life a little bit easier and make your work a bit cleaner by solving these questions one at a time. Okay? It's kind of like if I were to tell you to, say, integrate some awful sum of functions. Let's just say like these functions are really bad, ugly looking functions. If you were stuck integrating this and you couldn't split up the sum because the integral didn't let you do that, it makes it quite a bit harder of a problem than if you could split it up into two integrals like this and then work on each on its own. Okay, so linearity is always a nice property, and this is really saying that I have a linear type property for these linear ordinary differential equations. And really, to be honest, this property is where these differential equations, well, this property and the fact that it holds for homogeneous, the homogeneous version, is where these solution or these differential equations get the name linear. Okay, so we'll now have one more example before I give you a kind of general method for trying to solve a certain class of differential equations that you will be tested on solving. Okay, find the general solution to this differential equation here, and then after you find that, find a function that solves the differential equation with the IVPs, this and this. Or sorry, just IVs for initial values, but the S should be small. Okay, so this begs the question, how do I solve this? When I tried to do this with a different case earlier, you just kind of guessed the right answer, and that seems unfair, especially if we as the students are not allowed to do it in the class. So how can we go about doing this? So if I want to find the general solution, what do I do? Again, I first find the solution to the complementary equation, this homogeneous differential equation here. So notice typo, this needs to be y. It doesn't have to be, you could still solve it without the y, but For the problem that I had in mind, I want this to be y, and I want a 2 here. Okay, so to do this, the first thing I do again is find the characteristic polynomial. So I want p of r, and this is simply going to be r squared minus 2r plus 1. And I want to find the zeros of this to find the eigenvalues. So here, we do want to kind of show our work. We just don't want to say, here they are, because you're not supposed to be using calculators like that. So here we get that this thing implies that this has to be 0 just from factoring this out. Or in other words, this tells us that r is equal to 1, and this is a repeated root. Okie dokie. So how do we handle the repeated root case? Well, in the case of repeated roots, the solution to the homogeneous equation, so I'll just call it YH, this thing in general will simply be arbitrary constant e to the, in this case, 1 times x. So x plus a c times 2 times x e to the x. And of course, if you want, you can factor out the x like is done in the one theorem in the text, but I kind of prefer it written like this. It's personal choice here. Okay, so now that I have the homogeneous equation, I now need to find an equation for this whole thing here. Well, let's just kind of think this out. Last time I just let y be equal to all this stuff on the other side of the equation. Would that work here? Well, it would give me the stuff on that side right here, right? But when I take its derivative, that messes things up. So I can't let y be negative 3 minus x plus x squared. But notice something. If I let y be some arbitrary polynomial. Now the key thing is I don't know this polynomial, but I know its second order. So if I let y have this form, then when I take its first derivative and its second derivative and plug it into here, this whole expression will simply be a polynomial, right? And then the differential equation simply becomes polynomial equals polynomial. So I don't know the coefficient on the left-hand side, but what I can do is I can set the coefficients of the various powers of x equal to each other, get a system of equations, and solve for a, b, and c. That's precisely what I'm going to do here. Okay, so I'm making this ansatz here, and if this is true, then I get y prime is equal to just 2a x plus b, and I simply get that y double prime is equal to 2a. Okay, so if I make that assumption, that implies the stuff down here, and this tells me that my differential equation, y double prime minus 2y prime plus y, this side of the differential equation simplifies to simply be, well, let's just plug it in. Here I'm going to get a 2a for the constant term from here, so 2a. And then I'm going to get a minus 2 times this, so let's just expand that out. So I'll get a minus 4ax. So that's from this first term here. And I'm going to get minus 2b. Oops, or not 2e. That is the question. And then I just add this y term in. So let me just copy the y term and throw it over here. Okay. So I get this when I evaluate the left-hand side. And ultimately, I want this to be equal to the other polynomial. But let's just clean this up real quick. So from here, if I clean this up, and simplify everything out, I will find that I simply just get an ax squared, because that is my only x term, or sorry, x squared term. And then for my x terms, I can say, hey, look, here I have a minus 4a, and here I have a b. So I'm just going to write this as b minus 4a times x. And then I have a constant term, and that constant term I'm just going to write as 2a minus 2b plus c. Okay, so how this helps me is now I have that if y is of this form, then this differential equation here would then turn into this statement that this polynomial is simply equal to this thing here. Okay, This needs to be equal to this. So now what do I do? Well, this is really a linear algebra problem, right? Here I have two polynomials, they're equal, so that tells me that the coefficients have to be equal. So just setting the coefficients equal to each other, I immediately get that this a coefficient has to be equal to 1. That's useful. And from the second one, I get b minus 4a has to be equal to minus 1. And here I can simplify this for b, right? I can plug in the 1 for a, and then I can add the 4. So this tells me b has to be equal to 3. Okay? And then finally, the last equation, that tells me that 2a, which I know a is 1, but just for completion here, minus 2b, which I know b is 3, plus c, this thing has to be equal to negative 3. Okay, so if you then plug in the values for a and b into here and solve for c, you can find immediately that the c has to be equal to 1. Okay, so if you put all this together and kind of zoom out a bit, if you put all this together, this tells me that if y is of this solution, then if a is 1, b is 3, and c is 1, then this thing is actually a solution to the differential equation. Okay, so from this work, we can thus put all this together and we can write that y sub p is equal to, I'm using p for particular solution again, just FYI, is x squared plus 3x plus 1. Okay, so if I put all this together, my general solution would be this thing plus the homogeneous solution. So let's clean this up a bit and then come right back. Okay, just put that work over here. So putting this together, my general solution, which I will call y sub g, or if you're writing it out, you could say the general solution is and write it and box it in. But this thing is simply going to be this quantity here plus the other one. So cleaning that up there, that is my general solution. Okay, pretty straightforward. For the second bit, we want to apply these two initial conditions here. So that's also pretty straightforward. So applying these conditions, all I do is plug in 0 and set the equation equal to 2, and then plug in, take the derivative, then plug in 0 and set it equal to 1. So let's just do this work here and kind of speed it up so you don't have to sit through all the little details. Okay, so now I have my C1 and C2, so if I zoom out, so from here, just to kind of separate them out, I can conclude that my solution to the initial value problem will simply be y is equal to the thing that I had here as it stood. Oops, I do not want to copy it that way. The thing that I had here, and then to this, I want to subtract a minus 3e to the x, and then to this I want to add a 1x e to the x. Okay, so just cleaning up a little bit, here it is in slide form, and this is example 3.5.2 in Trench. Okay, so it turns out that, hey, I did this method, it worked here. That doesn't guarantee that this method will always work, and what do I do if it's cubic? What do I do if it's something else, right? Well, let's give a kind of statement of an algorithm that you can use to solve certain ones of these equations. And in the next lecture, we'll extend that, or the scope of which that method works, by showing a different ansatz for kind of more general cases here. Okay, so to solve a differential equation of this form, so here I have a linear second order differential equation. And for the non-homogeneity bit, I have this term over here where I have a n x to the n, there it goes, a n minus 1, x to the n minus 1. So this thing, if I just look at it, that is just an nth degree polynomial with arbitrary coefficients. Okay, so if I want to solve something that looks like this, the first thing I do is I find the general solution to the complementary equation. We know how to do this. We have a theorem for what these solutions look like, and to be honest, you should be able to derive the solution to this after you've seen it a couple times, so make sure you know that, because I might ask you on the midterm or the final to actually derive one of those solutions. I might not, but I might. Okay, so after we have this complementary general solution for the complementary equation, then what do? Well, I make the ansatz that y sub p is going to be an arbitrary polynomial of this form here. Full of little typos today, that'll be fixed. But we assume it's an arbitrary polynomial of this form, where in my choice, okay, there we go. Where in my choice for picking which order of the polynomial to pick over here, I pick the order of the polynomial to be the same as the order of the original polynomials that I had over here. Okay, so after I make this ansatz, what I do is I take this proposed solution and I plug it into here to see what would need to be true for this to be a solution. So this is my guess. Does it work? Well, I put it in the original ordinary differential equation, and when I do that, I get a polynomial over here is equal to a polynomial over here. So then I set the coefficients of the two polynomials equal to each other, namely the coefficient to x to the n to the x to the nth one over here, etc. And then I want to solve that linear system for the coefficients a n all the way up to a naught. And once I do that, I will have found y sub p. So kind of a note of convenience here, so to speak. Notice that these other terms here are higher derivatives of y, right? So the only term that'll have an a or x to the n power will simply be this term c a n or capital A n x to the n. So when you go to try to solve these, you don't need to set up the matrix system to try to solve it. You can if you really want to, but the back substitution will already be sitting there for you if you start by trying to find this coefficient a n by using the nth term here and then use the nth minus 1, etc. And that's exactly what I did in my work over here, right? I started with the squared and then the x and then the constant. If you do that, this back substitution trick will always work if you have differential equations of this form, okay? If you have something different, it might not work, but yeah, for these ones, it does work. So keep that in mind to make your life a little bit easier when working out those problems. Okay, and then once I solve that linear system and have y sub p, then from the theorem that we proved today, the 5.3.2, I know that the general solution to the differential equation of this form will simply be the sum of the general solution for the complementary equation, so the one that I found up here, plus this y sub p that I found here. Okay, so this method of guess a functional form and then see if it works is quite robust, but there's kind of an art to picking the right functional form for different equations. But generally speaking, you almost always, like you can, but oftentimes you won't go wrong by choosing an infinite sum of terms that look like this. We're probably not going to be able to have time to do that for this course, but if I find that I have downtime in one of the lectures, I might try to throw that in. It's very interesting to see, and it's quite useful in practice. Okay, so TLDR from this lecture, we can now solve equations like this, and we can now solve equations of this form. Okay. In the next lecture, we're going to extend the form or the functional form for these forcing terms to include multiplication of this polynomial by an exponential term. And in the subsequent lecture after that, we will also add some sine and cosine terms as well. Okay, so that's what you have to look forward to in the next two lectures this week. Well, then there's lecture 9, which will be about initial IVPs and BVPs, but I'll introduce that material once we get there. Okay, so I want you to read sections 5.2 and 5.3. So I strongly look the lowercase I threw me off. But I strongly recommend looking at the examples that I skipped for both sections. In particular, in 5.2, they give examples of those 3 different cases where I have 2 real roots, 1 real root, or 2 complex conjugate pair of roots. So good practice would be to look at those examples. And some of the examples in 5.3 can give you some more practice with this algorithm here. Okay, so that's basically what you should understand from this lecture and the last half of the previous lecture. And again, for practice problems, this is the recommended problem set for 5.2, and this is the recommended problem set for 5.3. Standard, don't do all the questions type thing. Okay, so meme. Guess the form of the particular solution, found a solution of that form. You would be surprised for how many cases this method actually works, but you do have to be able to pick a particular form that actually works. So if you just guess random stuff, it's probably not going to work, but if you guess the right random stuff, it will work. Okay, so we'll talk more about that later, and I will talk to you later.